We are focusing primarily on targets placed due to Pacific Shift. So our team includes McElwain, who's in charge of performance and aerodynamics, Joshua Waltz, who's in charge of propulsion, Max Starkle is in charge of structures, Nicholas Arnold, who's in charge of weight and balance, Rayanne, who's in charge of stability and control, Van Poller, who's in charge of systems and crew, and Kate Sjostrom, who's our COTIA lead. Before we begin talking about the aircraft, I would like to discuss a little bit about why we need this aircraft. Currently, our fleet is heavily reliant on B-52 and B-1. These are both conventional style aircraft, which means that they are highly susceptible to integrated air defenses. Additionally, both of them are planning to enter retirement or begin retiring in 2040. Our most recent bomber is the B-2, which is planning to enter retirement around 2060 and was limited to a production run of 22 of those. One has crashed and one is currently in reserves for training. So in addition to losing a significant amount of our long-range striker fleet beginning in 2040, and a lot of our fleet not being low observable, we need to consider the additional range required by the Pacific Shift, which began in 2011. This range requirement drove the chart you see up here. This is a 4,000-mile combat radius, assuming you launched from Anderson or Diego Garcia. Only the B-52 currently has the range to meet this range requirement, and again, it's going to be retiring in 2040 as a conventional style aircraft. So we took these constraints, we looked at what's going to be required to hit these targets in this area, and we came up with an 8,500-mile range for our aircraft. This allows for some lateral movement to avoid areas where detection risk is high. We also included a 30,000-pound payload. This was driven by the YB-25, which is a massive ordnance penetrator, because we wanted to be able to defeat any hardened bunkers that we may encounter as a target. So we applied all of these requirements that we developed, and we came up with the constraint diagram you see here. As you can see, we plotted it with our comparables as well. We have the lightest wing loading of all of our comparables. This is due primarily to the fact that we are currently oversized. Our initial weight estimates were about 450,000 pounds, and currently we're sitting closer to 350,000 pounds. So we're looking at doing a resizing in the beginning of the next semester to improve our wing loading, so that we will shift from where we currently are to right about here. This should significantly improve our performance and our ability to handle high-stress situations. Talking a bit more about the low observable aspect of our design, we had some initial shaping concerns. These were the primary concern for us was a blended wing tailless body. We didn't want to have any reflection coming off of the tail. We also wanted to use no 90-degree angles whatsoever in our design. And we wanted to have S-ducting on the inlet nozzles to hide the compressor face from incoming radar. In addition to these shaping requirements, we also included a few analysis of we also looked at a variety of materials capable of absorbing or obscuring radar and infrared signals. You can see these listed here. But on to the more meaty stuff, I will hand it off to Michael, who will discuss more of the design with respect to aerodynamics.
Thank you, John. So the first task that needed to happen, obviously, was to pick out an airfoil. We needed an airfoil that had good performance characteristics, as well as to help delay the critical Mach number as high as possible. Thus, eventually what came out was the Warman FX-80080 airfoil. This airfoil has a 2.2% camber, as well as an 8.1% thickness ratio. With this thickness ratio, combined with a 42.75-degree leading edge sweep, we were able to delay the critical Mach number over the wing to 0.843. As you can see on your left here, that is the picture of the airfoil cross-section. And on your right is the two-dimensional airfoil CL versus alpha plot. You may notice that we have a two-dimensional max CL of 1.25, as well as a stall angle of 11.25 degrees. But obviously we need a wing to fly. So the 2D airfoil data needed to be converted to a three-dimensional wing data using Brandt's methods. The three-dimensional here is plotted in orange compared to the two-dimensional data that was on the previous plot. You can see the comparison here. When we have our wing data, we have a new max CL of 0.99, as well as a new alpha stall of 11.5, which increased slightly. We also have a alpha zero lift of -3.4. So So our next slide shows a simple schematic of our YB-25. We have a 180-foot wingspan as well as a 30-foot chord. And at the bottom, you can see the leading edge sweep that I talked about. These were all optimized to fit to maximize most of our performance requirements that we had for the YB-25. But as you can see, we don't have a conventional aircraft. We have a blended wing body design. So we needed to take that three-dimensional wing data and somehow incorporate the effects that the body had on the aircraft. So using nickelized methods, in here in blue, we have the clean configuration of our aircraft. This does use nickelized methods, who has a blended wing body model. We have a new stall of 1.26. We have a new CL max of 1.26, excuse me, and a alpha stall of roughly the same 11.5 degrees. The tip there, that is where the aircraft stalls. You may notice there is no data after the stall angle. That is because Nikolai does not accurately model what happens after the stall regime. And the orange line up there is with our control surfaces deflected, our flaps along the trailing edge. We assume that we had flaps along the entire trailing edge of our wing, save for 4.5 feet from the wingtips inward. The new parameters with our flaps at takeoff and landing are there, with the CL max of 1.6 and a stall which brings it down to 10 degrees. So on the same note, we have the drag polar for the clean and dirty configuration as well. The same, clean is blue and the flap configuration is in orange with the trend lines included. At the bottom, we do have a drag component breakdown. To note, the body, wing, and miscellaneous, which includes the fuselage and intake bumps, are at the cruise condition of 40,000 feet. The landing gear and flap deflection drag are at takeoff and landing. So we have the lift to drag as the Mach increases. The blue is plotted at sea level, and the orange is the cruise condition at 40,000 feet. As I mentioned before, we have a critical Mach number over the wing of 0.843, but unfortunately our fuselage is a lot thicker than our wing, and our fuselage pops the critical Mach number at 0.77. And so we had to set our cruise condition to 0.75 on that vertical line there in order to stay away from the wave drag, which accounts for the steep drop in L over D right past the 0.75 line there. Our lift to drag at cruise, assuming the max weight, if we just got refueled in midair, is 19.1. So here we have the final preliminary design characteristics in the first column on the left. It is plotted versus the Avro Vulcan as well as the B-2 Spirit, as they are the most comparable aircraft to the ones that we have designed. Most notably is the Oswald's efficiency factor, which is fairly high, as you may notice. This is using the conventional wing method, as that is the most reliable that we could find, and any blended wing body method was unstable or very highly unreliable. But before we can even fly, we need enough power to get off the ground. So I will hand it over to Josh for propulsion.
Thank you, Mike. The first thing that we looked at when we were picking our engines was we wanted a low TSFC value. This was because of our very long range requirements. We also wanted a thrust to weight that was similar to many of our comparable aircraft. And some of the things that we excluded when we were first looking at engines was we excluded high bypass ratio turbofans because we are going to be S-ducting the engines for low observability, and the pressure variations along the wall can tear apart the fan of a high bypass ratio turbofan. So some of the add-ons that we considered because of our high weight was an afterburner system, but this was rejected because of the size and complexity of the system. We also looked at water injection for the engines, but we decided against this because we couldn't find any models that accurately simulated how much thrust we would get from that system. We also considered taking off without full fuel, and this is ultimately what we decided on. We will be taking off at a 0.73 fuel fraction and fuel weight, 73% fuel weight, excuse me. And we will be refueling once we get up into the air. We ended up with the F101-102 engine from GE that is pictured here, and we will be removing the afterburner. And we updated this engine using the elements of propulsion technology levels. And we ended up with a sea level static thrust of just under 20,000 pounds per engine and a TSFC of 0.5618. Here you can see the different parameters of the engine, TSFC and thrust, plotted against Mach number, throttle ratio, and altitude. As Mach number increases, our TSFC increases, and as throttle ratio increases, our TSFC increases. And as altitude increases, our TSFC decreases until the isothermal region of around 35,000 feet, excuse me. And thrust decreases with altitude as well. The inlet and diffuser combination, we found the inlet size using the perf program, and we found that at cruise we needed about 7 square feet per engine, and we upped this to 10 square feet per engine for higher performance at low Mach numbers and low altitudes. We S-ducted the inlet or diffuser to hide the compressor face. As we said before, we included turning vanes and trip strips to limit the pooling, and we found that our ratio of vertical offset was a little bit higher than we expected, and so we are going to be needing to do some research based on the report, the AIAA report that outlines the vertical offset. We are also going to be using blow-in doors and these on takeoff, and these were sized using the PERF program as well. The nozzle was designed to be very similar to the V2's nozzle system. We sized it using the PERF program as well and found that we needed 5.5 square feet per engine. This design also helps reduce the thermal cross-section of the aircraft by promoting mixing and hiding the hot air from view from the ground. And the bypass air also helps cool, from the engine, helps cool the exhaust as well. The nozzle will be including guide vanes and trip strips similar to the diffuser because of the geometry of our aircraft. And next I'll talk about the capabilities of our aircraft. Starting with specific excess power, plotted here in slough. This is using a max weight and assuming that the wings take all of the lift, so no contribution from the body. So it's a little bit conservative. You can see our cruise condition is just inside our envelope. And we also found that our service ceiling, defined as 100 feet per minute of excess power, is 42,800 feet, and our absolute ceiling is 43,500 feet. And this is slightly lower than our requirements of a service ceiling of 45,000 feet. The thrust available thrust required at sea level, you can see that we have a lower velocity limit of Mach 0.11 and an upper velocity limit of 0.81. And you can see that we have plenty of extra thrust at sea level for taking off and maneuvering low to the ground. But at cruise, we have a lower velocity limit of 0.53 and an upper velocity limit of 0.76. You can see that our cruise condition is just in our limit, and we would need 85% of our thrust available to cruise at this condition. Lastly, for me, we have range and endurance plotted at different payload weights. At our max payload of 30,000 pounds, we have a range of 10,400 miles. This is much higher than our requirement, and this is also assuming a cruise condition and our max fuel weight of 191,000 pounds. Next, I'll hand it back to Mike for takeoff analysis.
Thank you, Josh. So using Nikolai's methods, he breaks down the takeoff analysis into 4 different distances: the ground roll, transition, rotation, as well as the climb distance. It should also be noted that we have the normal 50-foot obstacle at the end of our runway that we need to clear. At the bottom, you can see the breakdown for each distance, but ultimately on a dry runway, we have a takeoff distance of 6,377 feet. This is, though, with the 73% fuel weight that Josh talked about earlier. Our rotation angle for climb is 5.4 degrees. And with the 73% fuel weight in our aircraft, we have a stall velocity of 177 feet per second, roughly 105 knots. Nikolai does use the 1.2 factor for the takeoff velocity from the stall velocity. Thus, we have a total takeoff velocity of 213 feet per second, about 126 knots there. But after takeoff, we need to land sometime. So again, Nikolai breaks it down, but this time he breaks it down in 3 different sections: the air distance, the free roll, and the braking distance. Again, their components are listed below. But ultimately, on a dry runway, we have a total landing distance of 3,701 feet. This is 201 feet above our required landing distance, but Nikolai also does assume half fuel weight in our aircraft in case the mission gets aborted halfway through the flight, or the target is a lot less than the maximum range for the YB-25. We have, again, the 50-foot obstacle on your left there that we need to clear. Over the 50-foot obstacle, we have a 1.3 factor for the stall velocity, which is 163 feet per second, assuming the aircraft has the half fuel in it. But on the touchdown, right there by the free roll, is a 1.15 factor from the stall velocity, which gives us a touchdown velocity of 188 feet per second, about 111 knots. So in the air, we have our maneuvering diagram. The lines are plotted in constant G loading, while the black is plotted in constant turn radius. The red box that you see there is what our aircraft is capable of doing, with the left being the maximum lift that our aircraft can achieve, the top being the maximum G loading that we can pull, and the right being the maximum velocity with the amount of thrust that we have. And on the bottom, we have the G loading that is pulled when our aircraft banks a certain degree listed there. But in order to pull all those Gs, we need structures to support that. So Kate will be here to talk about structures.
Thank you, Michael. So in order to determine our structure layout and spacing, we researched the structure of other bombers, such as the B-1 and the B-2. The primary forces we considered were the weights of the bomb bay and the engines, and the forces of flight and landing. Here is a diagram showing our internal layout. Centered in the aircraft is the bomb bay, with the payload highlighted in bright green. On either side of the bomb bay, we have the engines, highlighted in blue, and outboard of the engines are the landing gears, highlighted in red. The green boxes on the wingtips are the spots allocated for the laser systems, and all of the light blue indicates fuel tanks. Though 2 have been omitted for clarity, those 2 are located above the engines. We'll be using 3 different materials for our structure: titanium, fiberglass-coated aluminum, and an advanced carbon composite. Titanium will be used for the wing mounts because it is lightweight, strong, and won't corrode when it comes in contact with the composite. Aluminum will be used for all longerons and bulkheads, though it will have to be coated in fiberglass to prevent corrosion when it comes in contact with the skin. Aluminum was chosen because it's weldable, strong, and commonly used in aviation, making it easier to manufacture aircraft components. All spars, ribs, the skin, and the rear bulkheads will be made out of an advanced carbon composite that provides good strength, absorbs radar waves, and is lightweight. This composite is currently under development by NASA and Boeing, specifically for blended wing-body aircraft. It has already undergone extensive testing where it has performed phenomenally. It is comprised of an 8-layer multi-directional carbon skin that is supported by foam stiffeners and carbon stringers. These are stitched on in a grid pattern and provide the strength of the material. It also provides damage resistance because any damage to the skin can't propagate beyond the stitch rows. This composite is also easier to manufacture than traditional composites. And now I'll pass it off to Max, who will discuss the other aspects of the structure.
Thanks, Kate. Okay, so when we started going over what we're going to do for the structure, we had to figure out what kind of G loading we were going to do. Based off of the mil-spec center, the research into comparable craft, we decided to do a +3 -1 G loading configuration. Once this was completed, we began to design the actual structure inside the body. We decided to do the front 9 frames in aluminum and the back 3 in composite. This is mostly the back 3 being there for aerodynamic shaping purposes, less for support purposes. The overall structure was analyzed using shear bending and buckling equations in order to make sure that it was able to handle a +3 -1g loading configuration, and the skin was analyzed using a semi-monocoque approach. Once that was done, we started figuring out what we're going to need for as far as a keel. And we decided that we were going to run the keel over the top of the bomb bay in order to, 1, provide a mounting point for the YB-25 because it's quite large, and 2, because of the benefits for stiffness and for load path integration for the structure. Talking more about the bomb bay itself, it's 16 feet wide, 22 feet long, and 8 feet tall. It's designed to hold 2 rotary launchers, several conventional racks, or 1 YB-25 mounted directly onto the keel. The rotary launcher sizing for the bomb bay, we made the bomb bay the size it is in order to hold a maximum load of 16 Mark 84 JDAMs in the 2 rotary launchers with their larger fin configuration of 25.3 inches. This allows for 7.7 inches of clearance per rotary launcher in order to drop the payload. Once that was done, we moved on to the wing body attachment point. We decided to use titanium for the wing body attachment point as we were using composites for the wing, knowing that the composites and most aluminums and steels don't really get along with each other very well. Composites cause an effect called galvanic corrosion due to the difference in electronegativity of the 2 materials, but using titanium we surpass that and don't have that problem. So the composite spars are mounted into 2 flange-like structures and epoxied in, then bolted through with 8 1-inch titanium bolts shown above in the configuration there. And then they were analyzed for tearing, shear, and bearing and shear and tear out up to 3 Gs of loading as shown there. Finally, we went into designing the wing. We started looking at what conventional other bombers use for their spar design. We decided to use 2 spars based off of the other bombers we'd researched, and then we did some we looked into the CP plot for the wing to see what the different loading configurations would be on the spars. We designed the front spar to be mostly for aerodynamic shaping purposes, and the rear spar was placed where it is for control surface sizing. We moved into rib design after that. We looked at our comparables, mostly the B2, and based our 20 rib design on that. We were analyzing that afterwards, figured out what the rib thickness was based off the shear flow, and then looked at what the skin design would be. So based on our rib spacing, we found that the buckling coefficient for the skin would be approaching infinity, and that we would be able to handle all the loads needed for flight. We then analyzed all of these for shear, made sure that it was going to be okay, and bending moment up to 3 Gs of loading with a 1.25 factor of safety. Lastly, we looked into our gust loading for the airplane. We adjusted our cruise, dive, and maneuver gust lines based off of our cruising altitude of 40,000 feet and plotted them as shown versus our VN diagram. As you can see, we really don't have any effect to our structural loading as far as gust loading goes for our plane. And next I'll hand off to Rand for stability control.
Thank you, Max. So to begin our stability and control design, we compared similar tailless aircraft and bombers to trailing edge surfaces to see where our bomber would lie. As you can see, the YB-25 falls within the range of similar aircraft, such as the B2 and the YB-49, with a 35% chord trailing edge surface and 65% span trailing edge surface. For our control surfaces, we chose to use both elevons and split drag rudders. The elevons are for pitch and roll control, and the split drag rudders act as both elevons or ailerons and as drag devices for yaw control, and flaps are deflected both up and down. As for longitudinal stability, the YB-25 is statically stable as long as there's 4.6% total fuel remaining and as long as the fuel burn order is followed. The goal of 5% static margin as set by Nikolai for tailless and subsonic aircraft was met or exceeded by the YB-25 for the majority of the mission. As you can see, our CG does shift as fuel is burned and payload is dropped. This chart shows 4 different loading configurations for the YB-25, such as full payload, no payload, the rotary launcher, and the MOP. And as you can see, the CG does cross the aerodynamic center at one location, but that is where the 4.6% total fuel is remaining. Next for Brian for lateral directional stability.
Thank you, Rian. In terms of our lateral directional stability, the YB-25 is unstable in yaw under side slip. The other three stability parameters within these directions are stable, however, they are outside of the respective ranges for a typical aircraft. This is understandable because we are using a blended wing body where this can happen. Any stability issues that this plane will have will be addressed in the detailed design phase of this aircraft, where we will introduce a full fly-by-wire system to handle any kind of stability issues. In terms of a crosswinds on landing scenario, control authority can be easily used to counter the yaw component of the crosswind, where we don't even have to deflect one of the split drag wires 1 degree in order to counter the moment that's generated by it. However, we cannot counter the roll moment that is generated by the crosswind at this time. This is due to the plane's very large planform area and due to the very high degree of swept wings, forward swept wings. These, however, will change when we go into the detailed design phase of this aircraft, so we are not concerned at this time about this. In an engine out scenario, the most limiting case would be where 2 engines are out on one side during a takeoff. And as you can see, using the control authority listed below, the aircraft can handle this scenario without any problems. In terms of high altitude control, where there is low air density, as prescribed in the MIL handbook, a class 3 aircraft, which is what we fall under, must be able to roll 30 degrees in 1.5 seconds, and using just one of these split drag rudders, we are able to do this. Now handing off to Van for systems and crew.
Thank you, Brian. So the YB-25 requires 2 pilots, both of whom sit offset from the symmetric center line of the aircraft. For an aircraft of this type, Roscom outlined several military requirements for the positioning of the pilots, the first being the position of the pilot's eyes to the front windscreen. This distance must fall in the range of 1.64 to approximately 1.97. In addition to that, both pilots must maintain a 135-degree field of view from forward outboard of the aircraft and a 30-degree field of view forward inboard of the aircraft, as well as maintaining a 20-degree field of vision from level sight up and a 15-degree field of vision from level sight down. As you can see from these images, we are in complete compliance with these requirements. Specifically, the bottom image, the green cone highlights the complete vertical field of vision of the pilots, wherein we are over exceeding the requirements outlined by Roscom. For the safety of the pilots, the YB-25 utilizes 2 ACES-5 ejection seats. Now these seats are employable from speeds anywhere from 0 to 1,000 feet per second and at altitudes anywhere from 0 to 60,000 feet per second. The yellow panel shown in the image above outlines the surface of the YB-25 that will be blown off to provide a safe egress path for both pilots. The YB-25 is planning on using a radar that is based on the same one utilized in the B-2. This is a ground scanning radar known as the AN/APQ-181, which maps out terrains and targets therein along an aircraft's flight trajectory. Now, the YB-25, I say based on the B-2 because we are accepting that there will be a large transition in technology advancements from now to the point that the YB-25 is actually developed. Therefore, we are assuming that the radar used in the YB-25 will not consume any more space, volume, or pardon me, weight, or power than the one utilized in the B-2 with higher performance values. In addition to that, while the YB-25 is a long-range strike bomber, we would be remiss if we did not take into consideration air-to-air situations. The Air Force is currently doing research on directed high-energy systems. These would be employed on fighter jets to provide air-to-air defenses against incoming missiles. We are planning on utilizing the same technology on board the YB-25, specifically at the wingtips as shown in this image. These systems would be utilized to provide the YB-25 with some integrated air defense systems, were to come in contact with air missiles. At this point, I will pass it off to Nick to go over the YB-25's field capacity.
Thank you, Van. So as mentioned earlier in the presentation by Kate, Our fuel system comprises of 5 fuel tanks, one located in each wing, one located above each engine bay, and a big one directly behind the cockpit. The total volume of these 3 tanks allows us to carry 225,000 pounds of fuel unbaffled. However, when baffling is taken into account, that reduces our fuel capacity to 191,000 pounds of fuel. It is assumed that roughly 20,000 pounds of this capacity will be devoted towards contrail eliminating substances. The numbers shown on the screen also denote the fuel burn pattern that we are prescribing for regular missions, starting with burning fuel in the wing tanks and adding the engine and cockpit tanks as the flight progresses. This fuel burn pattern was selected to push the CG of the aircraft forward up until the point of payload release, allowing the plane to remain stable during the release of a 30,000 pound MOP. With this fuel configuration, we were concerned about one fuel blockage scenario. This scenario arises when 100% of fuel is trapped in the wing tanks, which comprise both our largest tanks and the furthest from the CG in the rear direction. However, since we are using these tanks immediately on takeoff, it is assumed that the only way we can achieve 100% blocked fuel in the fuel tanks is after aerial refueling, which we do to recover the 27% fuel we do not take off with, or possibly for a strike from the continental US to Southeast Asia. If this scenario were to occur, we are able to burn 70% of the fuel in the remaining 3 tanks to achieve a range of 4,500 miles to find a safe location to land. If we have already released our payload, we are only able to burn 38% of the remaining fuel in the forward tanks, with a range of about 2,500 miles to find a safe landing. Talking about landing, it's generally necessary to have landing gear. For our landing gear, we chose a 90-10 loading ratio. This was selected because at our initial weight estimates of 450,000 pounds, the dynamic loading on the nose gear was too high to sustain an 85-15 loading ratio, so we shifted more weight back onto the main gear for the 90-10 loading ratio. The first gear that was positioned was the nose gear. This was positioned to coincide with the first structural member capable of bearing loads in an aborted takeoff, which was located 4 feet back from the nose. Our main gear was then located at 46.5 feet back from the nose to yield the 90-10 ratio. Due to the presence of the bomb bay and engines, our main gear was forced wide out on the wings at 20.5 feet from the center line of the aircraft. Using the 90-10 loading ratio, we were able to use the same tire for both the nose gear and the main gear. This is assuming that the nose gear has a 2-tire configuration in the twin configuration, and the main gear has 4 tires in the twin tandem configuration. For landing gear, there are some critical angles and critical weights that we needed to analyze. First of these weights is the tip-back angle, which is the point when the CG crosses the landing gear. For us, this angle fell at 20.4 degrees, which allows us to easily meet our takeoff rotation of 5.4 degrees. Our tail strike angle, which was slightly less than our tip back at 19.8 degrees, also allows us to easily achieve the 5.4 degree takeoff rotation. With our landing gear being placed so far out, our turnover angle was extremely favorable at 15.1 degrees, which is about half of what it is for aircraft in a similar weight range. However, most of these aircraft are conventional and have narrower landing gear configurations. The first of our critical weights was the takeoff weight. This we estimated as around 345,000 pounds. We are easily able to accommodate this, being able to sustain up to 381,000 pounds loading for an aborted takeoff and 408,000 pounds in static loading on the landing gear before tire failure. I will now hand it back to John for risks and conclusions.
Thank you, Nick. So the major risks regarding our project, the first one is the use of the warp and airfoil, which has not been used elsewhere. This means that we will need to investigate the aerodynamic performance of it to evaluate and confirm that the predictions are correct. Additionally, as mentioned earlier, we will be needing to evaluate the S-ducting to confirm that it will function as predicted and allows the proper amount of airflow. The final major concern for us is the use of this advanced composite. Because it's currently under development and does make up a significant portion of our structure, we need to keep a close eye on the development and make sure that no problems arise while it is being developed. In regards to compliance, it's been mentioned throughout the presentation that we are not fully compliant with all of our requirements. This is in part due to us being oversized, and also in part due to some of the requirements to carry our payload. We are not compliant with the cruise Mach as a result of the need to carry our 2 rotary launchers. The ceiling and landing ground mount will be looked at during our resizing we are going to be performing next semester. So in regards to next semester, as I mentioned, we will be doing that resizing. We will also be requesting a change in the requirements to reduce our cruise Mach number so we would be able to meet that requirement. And we will be developing a wind tunnel test model to validate our performance and aerodynamic characteristics, as well as validate our stability control characteristics. With that, I would like to thank you for attending our presentation and ask if there are any questions.
I'm aerospace engineer, graduated here in 2015. I don't have too much to, I like the presentation overall. You guys all spoke very well, very clearly. You guys all matched, so that's cool. You know, you guys look like a team, so that's always good to see. I had a couple of questions on the systems. So you mentioned your energy defense system. Do you guys have your standard chaff flares or other means of taking out threats?
Yes, we will be utilizing these. However, we didn't want to just depend on one method because generally fighter aircraft or aircraft that come into air-to-air combat have a high level of maneuverability to counteract missiles. And along with those systems, we thought it was pertinent to come up with a primary means aside from that, given how slow and comparably unmaneuverable the YB-25 is.
Yeah, that's fair. I was just making sure you guys actually have that because you have to deal with other systems out there. And then, yeah, that was that one. And then also, it would have been nice to label on your the visibility what your sitting height is, what you actually used. So just to have that, and hopefully it's comparable to the B2, because you want to compare, since your aircraft is so similar to the B2, you want to make sure you guys are looking after that, so you prove like, okay, at least this makes sense. On your airfoil selection, like you said, it was a risk for sure. It would have been nice to have your other airfoils you looked at, and then say, this is why we chose this one, just like briefly. You don't have to spend a lot of time on it, so then you can kind of have a proof of why you guys decided to go with a higher risk airfoil over one that's already been used. And yeah, I mean, you guys obviously done research on stealth mechanisms and other things like that. And like, for example, like on your engine selection, you guys showed all the different engines you looked at. Kind of the same idea, but you should have done the airfoils too. Yeah, I don't think I had too much else than that. So overall, I thought it was pretty squared away, and it was a really interesting concept. I like it. So, thank you.
Hi guys, my name is Connor Warren, Mike Gerson. I graduated here in 2015. I'm astronautics in focus, and I've done flight test engineering and a little bit of rocket propulsion for about 2 years now. Well, year and a half, sorry. I just want to echo Garrison's comments though. Pretty good. You guys are well-rounded. It's a very good start, I think. You guys have covered a whole lot of bases. Like, I was really happy to see that you've identified your risks and what you need to address next time. One thing though I wanted to zero in though, for your material choice, especially that composite. Have you guys ever tried to send signals through a composite?
We haven't. However, I've been reading up on composite as part of stealth. I know that the epoxy acts as a dielectric. So that means it's not necessarily absorbing it, but it is slowing it down. The carbon would be the main absorber for that composite.
I just bring it up as something from past experience. I was part of IAA because I don't fly here, and that was a problem we had a lot with carbon fiber, was trying to send a signal through composites. So just for next semester, as a heads up, composites don't like to cooperate with signals.
Yeah.
So it's just something else to think about too for how are you going to position your radar, how are you going to shield it, and all that fun stuff. It's just to add on to your material compatibility.
Okay. Thank you.
I also wanted to zero in kind of on what Garrison brought up as well, the directed energy defense. Do you guys have the space for it?
We have the space. We set it aside. So we did set it aside on the wingtips. That was primarily to give it a good field of view. If we put it kind of in the fuselage, we were worried fuselage would get in the way of it being able to see what it needs to see.
So are you able to take out a threat directly behind you? Put it on with it?
It should. I mean, it's kind of one of those things we don't know what the system's going to look like, what it's going to be able to do, how much it's going to weigh. There's nothing available on the system right now. We just kind of set aside some space so that it could be incorporated.
So the reason I'm asking is because I wanted to know if you're going to store your batteries with it. Because I'm assuming you're powering it by batteries, or are you guys going to do something else?
So
I don't know if you guys got that.
Well, I'll hand it off to Van.
For that, we did make reservations for power consumption for the engine. However, if we did need additional batteries, we're going to store them inboard the aircraft to not add any more weight to our wing tips, especially that far back of our CG.
Okay, because that was all I was concerned about. Was if you guys are going to power the batteries, they would get very heavy very fast.
Yeah.
It's really a visual location.
We did find that much. We do know it's a large consumer of energy, so it would need a lot of power. We kind of talked about the use of rockets, I think is the traditional way they do it, but not generally a good way to do it on an airplane, I don't think.
Dr. Fabian might have something to
APUs and off-common gas turbines are much more efficient than batteries for what you need, and you can spin them up fast. And you got room for APUs.
Okay, I just wanted to bring it up because there's a lot of directed energy options, especially in today's world. So it's kind of, I was kind of curious too. Have you guys kind of picked like what route you guys are going to go? I mean, are you guys going to go for a hard kill? Are you guys going to go for a soft kill? I mean, there's a whole lot of ways to use directed energy weapon. I was just wondering if you guys thought about that yet.
The main problem, I don't know enough of it to know if it correlates with hard kill or soft kill, but the idea is to use the energy system to destroy the target system of the missile. So not to actually destroy or pre-detonate the munition part of it, but just to eliminate its ability to block and guide targets.
Okay, yeah, that's just a question. Awesome. That's good that you guys thought about that. I think that's most of what I had. The only other comments I had were a few others where I just kind of wish you had a little more methodology. Try to find a slide here, sorry. There were a couple where you're talking about, hold on, find the slide about one.
While I was looking for that, the only other thing that I just thought of was that it would have been nice to have you guys link towards one another a little bit more. So like early on, you mentioned the laser system, we hadn't seen that yet, and then it finally showed up at the end. That's just an example. So like just kind of like thinking ahead and back, so like especially when you like this actually was a slide. So it was mentioned on this slide the laser system, and I was like, I didn't know you guys had laser systems.
All of those organizational things, I got those.
Yeah, so I mean, just a little thing that helps, just because at least we can expect to see it later, so then I'm not just like, that's weird, okay. Hopefully they'll mention it later, or I'll ask about it, so other than that.
What? This is 57. Oh, I'll just write that. Okay, so I'm looking at 52. It's not the one I remember that I want to comment on, but there were a few things where you talked about drag, fuel, anyways, the point I'm getting at was just kind of seemed like there was a number, and I didn't quite understand how you got to it. So just as a request, if you could put the equation on there next time, just so I know how you got there, or a quick methodology. It's kind of leading off what Garrison was saying earlier. It's just for me, it helps me catch up because I'm not narrow. So there's some things where I'm just kind of, where this number comes from.
That was mostly for the lift and drag considerations.
Lift and drag and fuel pumping was actually the thing I was wondering about.
Okay.
I was just thinking, I don't know if you guys had time to address it, but it's something that I was kind of wondering, what could you pump the fuel around to adjust your CG? And it's just that can become a complicated problem real fast though. So I just wanted to know, I guess, a little bit more of what you guys have done, how far you have to get, or how far you have gone.
All right.
But that's mostly what I had. Overall, it's quite well done. You guys covered a lot of ground, I thought, and I'll see what you guys do next semester.
Thank you.
Alright, so my name is David. I also graduated here in 14. I am not an AE. Just a little new, so I only have a question and a point. So if you could turn to 57. So I may be wrong, but I think this is the first time I saw all of the requirements together in the same spot. So you guys covered a lot of ground, and you presented really well. But I think the major sticking point was I didn't have that data with the data you were presenting. It's helpful to have requirements right next to the data, because then you can just make a quick comparison. And it's easy to look at, and then I can pay attention to whatever you're saying. So that's just a quick point there. Logistics, it makes it easier for next time. Very good presentation. So now the question I'm going to ask, it's a little bit of a hard one, is those requirements in red. That happens a lot in industry. You're going to encounter that a lot, where your first cut, you miss some very big rules. So my question is, how are you going to move forward?
So as I mentioned earlier, we're looking at doing a resizing. This will significantly decrease our wing area, which means we should be producing significantly less drag. So we're hoping that will help boost our service cylinder where it needs to be. In addition to the as a result of this resizing, we're actually going to be losing another 40 to 50,000 pounds as the aerodynamic performance improves. So that will help our ground roll significantly. The only thing we can't really do anything about is the cruise mop. That's because our body thickness can't change. We have to be able to fit those rotary launchers in there somehow. So we've already been discussing and looking at what we're going to be doing as far as fixing this requirement, or that requirement compliance.
Go to 14. When you got to your cruise problem, and I mean, we didn't know what the true Mach requirement was, but hopefully there. 14. Sorry, I'm getting there. Okay, you got the steep drop off because of the fuselage. Is there anything you can change, or can you offer anything? When you're presenting it, it's like it's a dang cliff. So can you talk about it? You know, you want to offer some things, and you said redesigns, but to me, when you're on this chart, you talk about in the redesign, we're gonna try and figure some tricks out. Whatever they are, that's fine. Okay, but that is, I mean, you got this great airfoil, it's wonderful, except it doesn't really matter because something else is kicking you. Okay. So that's that guy. Go to 20. Yes. In the intro, there was mention of the S duct, and it was an S duct, and there was something said of why it was there. On this chart, it says there's S duct. What kind of engine do you have?
Turbofan.
Turbofan. What's the first thing on the turbofan? The fan. So what's the purpose of the S duct? High D what? The fan. The fan. Okay. So it was said in the intro and it was said on the chart, but think about what you got. You're hiding the fan, not the compressor. Okay. That's okay. That's the first rotating component that's going to cause radar reflections back. That's compressor support too. The fan support. Okay. So that's that. And you're so close to it. I only forgot that this thing's a turbofan engine. Just the only turbofan engine. They're in a turbojet in the list. Okay? Go to 23. You guys did great. It was absolutely fantastic. I enjoyed the heck out of it. Okay, there's your cruise condition. You don't have much piece of S left. You said you didn't include the blended wing body for performance. Any idea what % oomph that would give you on this plot to help you have some more margin?
I'm not actually sure how much that would give us. We'd have to run it again,
okay.
And figure out the method of how much lift and drag the body actually creates, and how much that would relieve the wing.
Even if you did a cruise condition only calc, and I understand why you don't want to try and do it for the whole stinking thing, but just to have the cruise condition crunched to know, hey, it buys me this much here. Either we could run it with higher power computers or whatever later, but to have that in your hip pocket is useful when you're kind of trapped. Okay, that was that. It's gamesmanship. I went to your maneuver flight diagram and I was going to ask, what's the storm penetration Mach number? What does that mean at 40,000 feet? It looks like your gust loading later on in the thing alleviates that. So that was one where it's like you're on a mission, you have to go, there could be lousy weather, and you're going to have to descend to get to a lower flight speed in order to get through the storm, and you're on a mission where you don't want to descend. Okay, so it's one of those, but it looks like you solved that. Go to 35. Okay, you guys are too close to this. There's 8 bolts numbered 1 through 8. There's a nifty picture over there on the right with 8 bolts, and I have no idea which one's which. Doesn't matter to me. I don't know. But there's 8 bolts listed on the left, and there's a picture on the right, and there's no numbers. Okay. So that's a quick chartsmanship thing where, does it matter? No. I'm not a structure dude. I could care less about bolts. But I'm going to get excited about bolt number 1. But I don't even know which one is bolt number 1. Okay, so just a little chartsmanship thing where it clears it up. Go to 48. And as I said, you guys did a great job. When I look at the field of view in the green, it looks like you got plenty of field of view. There's probably a spar up there on the top, to the right of that top of the field of view. And then I'm thinking about the pilot's legs and feet when you talk about the ejection system. For me, looking at this thing, it looks like the dude's going to lose his feet or his knees. Okay, because I'm looking at that seat going, well, maybe it angles back more, I don't know. But when that chart to the next chart, it looks like you don't want big feet. Okay, and so that's one of those ones where it's a great field of view, but you may want to give some of that up to help get the guy out. And I don't know the answer. It's just
it does go back a little bit.
It goes back.
I will consider that.
Okay. You see what I mean? But from chartsmanship, I'm looking at it going, well, you got knees, and it doesn't look like if you fly any airliners, you know about knees. Okay, that's that one. Let's see what else I got. Something else. Oh, 56. What's the technology readiness level of this composite? Okay, that's a typical question, a NASA technology readiness level. Is it a dreamland? Is it?
So I actually did this. I believe it was in the 4 or 5 because it's undergoing laboratory testing currently. Okay. So it hasn't been tested in the environment yet, but it has been tested in the lab.
Okay. How soon do you guys need to be in production?
We're looking at starting production probably around 2025.
Okay. Fingers crossed on that. There's lots of promises on things that never pan out. In my space prop, I tell them about TRLs and things can take 20 years. Okay, so watch out. All right. And I think that was the end of my markings. Overall, superb. You guys did a great job.
Thank you.
Thank you. It was fun.
Just to throw something on real quick too for that advanced composite, make sure you have backup plan.
Yes.
That's like where they go today.
Yeah, and I just had 2 last comments, I'm sorry. So the first one was you mentioned at the end the requirements you wanted to request to have changed. You need to be able to prove why. You can't just ask, because otherwise your sponsor or whoever's paying for it's like, I don't care. I want Mach 1.8. You have to come back and say, no, we can't do it because this. And then they're like, oh, okay, we'll be more willing to change it, you know. And then that also, I just asked that Dr. Fabian mentioned it. We never knew what you were going to want with the same production get-go, so you never really mentioned that, but this is something good. So, cool.
So let's answer their question. What's causing the drag rise in the fuselage?
The drag rise in the fuselage is the critical Mach number at 0.77 due to the thickness to chord ratio of the fuselage, which is driven primarily by the rotary launchers and the need to carry the Mach 8 force.
And so
we can't.
What doesn't scale? Because I look at B2 and it's got 0.85 critical and you're at 0.75. What's not scaling? What's the problem?
So the bomb bay is not scaling with respect to the rest of the aircraft. So we were able to scale down and scale up certain aspects in order to improve our performance, but the bomb bay cannot change. So the only way that we could overcome that and increase our thickness to chord ratio would be to have a fuselage of about 141 feet long, which is
more like a ball.
Yeah.
And less like a B2. When has the Air Force said they would like to put a directed energy weapon on a fighter? What year?
I don't know off the top of my head, man.
I don't know. I don't know either.
Yeah, you do. You read it.
I don't remember right now, sir. I know it's currently being tested on. It's either the Boeing 747, thank you, A45 frame, but they haven't gotten a scale version of it down that's even small enough to put in a fighter frame yet. So it's still very much in its infancy.
Might put it on your airplane before they put it on the fighter because you've got more room to play with.
Yes, sir.
Now, at this level, when the technology is still speculative, what's the only thing you care about?
We care about weight, volume, power consumption. I don't remember the other 3.
Data in and out, access,
field of view.
And field of view.
Okay. So if you're worried about those things and you left a hole, then other people get their act together, then you are ready to receive them. And so that's what affects you. There is a precedent for this, you know. On the B-35 and the B-49, they had gun turrets on the top and bottoms of the wings out near the tips. So there has been a precedent where a flying wing had to have defensive systems. And creating field of view and locating was a challenge, and they did it. Why do you want to put more fuel into the wing?
Ideally, we would distribute the load across the wing. That's kind of what a blended wing body is designed for, is a distributed load across the wings. Greatly reduces the moment felt by the body due to the wings and lift. And just generally improves the loading of the entire system.
So all that empty space out of the wing, we're going to make that wing smaller, fill that up, right?
Correct.
Did you guys compare your payload to what the G2 and B1 can use, or are you strictly in air to ground, or are you going to be able to do air to surface more there as well?
So we compared our payload to the B2. The B2 can carry up to 40,000 pounds. The reason that we're carrying the rotary launchers is to allow us to carry both AIM and AGM missiles. So we will have the ability to do not just interdiction, but also some limited kind of air to radar defense stuff. Pretty much anything that the B2 can carry, we can also carry, because the major constraint was that rotary launcher, which is what the B2 uses to carry the smart weapons.
Dr. Ayers, we're glad to have you here this morning. You have some experience with this class of airplane. Would you like to weigh in?
Oh, sure. I have 3 comments. One, I love anyone who designs bombers because it's job security. Second, as a bomber pilot with some experience, I like to go faster, not slower. I like to be more maneuverable, and I like my knees during if you get on the airplane with everything sort of operating, if you have to bail out, you want it to still operate. So it's a good thing. I thought it was excellent.
Thank you.
Thank you. Any comments from the audience?
Yeah, I have a question. So I'm Greg Bunting from Sandy Labs. So I'm not an aero once again. Early on you showed a picture of your range and it was centered on an Air Force base.
Correct.
But then you said you couldn't take off with full fuel. And so was that the range with takeoff, or are you assuming that you're refueling over your Air Force base? I guess is the question.
Pull that slide real quick.
You want to take the slide just to answer your question?
Okay. So the mission concept right now would be a launch from Whiteman. We would refuel over that listed Air Force base over Guam. And that would give us that range that you see there. The launching from Diego Garcia would limit us to a conventional payload. So we can launch from Diego Garcia with a conventional payload, but if we need anything more intimidating, we would have to launch from probably Whiteman and refuel over Guam.
Okay. And then just another question. I noticed your wingspan was larger than the planes you were replacing. Are you limiting yourself in some way there?
Yeah, we limited the wingspan to no greater than 200 feet. We wanted to keep it below that, just so we have somewhere to put it. It's 8 feet longer than the B2s, which is a fairly nominal amount, I think. When we do our resizing, we're probably actually going to lose some of that wingspan as well. Like we said, we originally were planning on carrying a lot more weight than we are currently.
Okay. And the third one was on the payloads. Is you kind of focused on one payload, just a statement that you said in the questions that you could do anything that the current planes can do. That'd be good in the presentation.
Okay. We'll do that next time. Thank you.
So I'm just a student here, but I have a few questions regarding the aerodynamics. The first one is that it was mentioned you guys would use 30 degrees faster deflection for takeoff and landing. But the problem with the flying wing is that since it doesn't have a tail, there's no way to correct the downward pitching moment of flaps, since you have flaps along the entire trunk and wing. So how are you going to correct that pitching moment?
I guess we didn't really look into too much of the downward pitching moment. We do have a plot of it,
right.
Not included on here, but with the 30-degree flap deflection, we saw that it didn't it affected too much. If not, we could pitch up the outer split flaps in order to help correct any sort of moment that we receive.
So like you might actually have to increase the span of the flaps so that you're concentrated towards the CG, because those flaps are going to act as elevators and push things down. My second question is regarding the critical Mach number of the blended wing fuselage.
Yes.
Is that a supercritical cross section?
It is not.
It's not.
It is not.
That could.
Yeah, because the fuselage is mainly driven by the cockpit, the field of view, as well as the bomb bay. So that was contributed to those two.
Yes. Oh, and third question, lift to drag ratio. What's your maximum lift to drag ratio?
The maximum lift to drag is 19.5, slightly below Mach 0.75.
From my knowledge, the Boeing 777 could lift to drag is like 22 at Mach 0.84. So, and you guys can find wing, so it could be more efficient.
Yes. When we redesign our wing, we'll be cutting off a lot of area, so our aspect ratio will increase a little bit, which will give us a lift to drag ratio we estimate about 21, 22.
Pretty impressive.
Thank you.
Log out and let the next team log in.